I'd like to introduce our next speaker. Carlos, you should be able to control the slides, I believe. So Carlos Rosales from TAC is going to talk to us about his work with Lorraine Olson at Rose Hulman Institute of Technology. And I thought some of Carlos's, the description in his abstract of the work, where he talks about the original naive attempts at improving its performance, kind of made me smile when I read it. I think a lot of the work of ECSSers is sort of in kind of fits and starts. You know, you're looking at this completely new code. You know, you don't know where to start. You try some things, they don't pan out. What we typically hear about on the calls is all the things that did pan out swimmingly, but there are a lot of steps to get to that sometimes. And so Carlos is going to talk about work substituting some original solvers in a legacy Fortran code with some more efficient implementations of mumps and blobs. So, Carlos, if you can take it away here, I'll mute the background again here just a moment.
Thanks, Nancy.
Presentation mode is now enabled.
So I hope everybody can hear me because my throat is kind of giving up on me, but I hope that we can get through this. If the sound is bad, Nancy, just let me know. I'm going to talk to you about a project that I started with Lorraine Olson. She works on novel ways to improve breast cancer detection techniques. And what Lorraine wanted to do was to stop using mammograms because they have the inconvenience of radiation, so they're only applied to people which are in certain groups of risk. And she wanted to use tissue stiffness measurements analyzed by software to tell us when there is a possibility of having a cancerous tissue in the breast. The code is very computationally intensive, and it works reasonably well in 2D. Actually, when they've done trials, the way that they can match experimental results is striking. But in 3 dimensions, they found that the code was fairly slow, and they wanted to get the most out of their SUs, like every user that we have. So what they did was they applied for ECSS support to essentially improve the the solver in the code. Let me go to the next slide. So the goals for ECSS were essentially substitute the custom solver that they had in their legacy code, which is a mix of Fortran 77, Fortran 90, and some of the things that I'm not quite sure what they actually are. Preferably, they would prefer to use mumps because it has fairly good support for skyline storage, and they're using skyline storage in their code. And the final user goal would be to have a 2x speed up in the system. But what Lorraine was more interested in than getting 2x speed up was into getting a solver in the code that was scalable, so that in the future she can make changes, she can scale up the operation that she has, and so on. So the actual goals were essentially to introduce a scalable solver, at least match current performance, and set the code up for further optimization by the group. So the 2x was would like to, but not a necessary goal. The original code structure was an MPI parallel code with very, very little communication, because essentially what she's doing is she's distributing load cases to every task, and every task is working independently. There's only a couple of global synchronization steps, and when we profiled the code, we saw that those were not very important with respect to total time, a very, very tiny fraction of total execution time. The average throughput was actually surprisingly good for a custom solver that was handmade, but it did not have any possibility of speeding up because it did have no threading. It didn't have any distributed solver for each set of loads. So it clearly needed a little bit of a refresher. In terms of I/O, this code has minimal output to disk, and the storage that they do in memory is fairly good, because they use a Skyline. The matrix is very, very sparse, so the amount of memory that they actually use is pretty small for the size of the matrices that they're using. So I was very happy with the I/O part of the code, and we just decided to go ahead and focus on this substitution of the solver. What the solver was doing originally, the custom solver that they had, was they had a main structure for the matrix that looks like a matrix with four submatrices in it. You could see a K, UU on the top left. That matrix is essentially static. It does not change with different loads. And then they have these BUF matrices that change with every load that the genetic algorithm is going to test. So you can essentially express these as an LDL factorization, and you can see the steps that they follow to solve that in this next slide. Essentially, they will factor K, obtain LDL, and store DNL. Then for every load, they will assemble BUF, and using it, they will obtain L12, L2, and D2. They will do a forward reduction to obtain an intermediate value, delta tilde, and then a back substitution to find U and F. And then they will repeat these as many times as necessary to complete the number of loads that they have. So this is actually fine. It's good in the sense that they reuse the factor for KUU all the time, and that saves them a lot of time, even though their implementation is not optimal. The challenge here is that if I want to change this now to a regular solver, most solvers will not provide me with the factor straight out. So the factors will be used internally, and with a second call to a solver in MUMPS, I can get my solution. Same thing will happen with Paradiso and several other solvers, but it's not particularly easy to just get the factors from the first step and not the solution, so that you can reuse them. So the first thing that that we did was to just say, well, look, this code is probably not very efficient anyway, so let's just substitute this whole solver by a single MUMPS call for every load, which means that we are factoring the full matrix, not only BUF, but we are factoring absolutely everything for every load that we're using, which is clearly a waste, but it should give us a good idea of whether this is viable or not. And then we started finding problems. Essentially, every task behaves completely independently of the rest. So we would have to use essentially a serial solver in every task to begin with, but we can't if we're going to use MUMPS, because MUMPS was always built as a parallel code, and it contains dummy MPI stubs even in the serial version. So you cannot use the serial version of MUMPS from MPI. On the other hand, we don't want all the tasks involved in the MUMPS solve, because the matrices that we're going to solve are too small to involve the 320, 640, 1080 task jobs that Lorraine usually runs. I mean, we might be able to use efficiently a few, but not 300. So what we did was just to do a little trick. We created an MPI communicator for each task, and we told MUMPS that its whole MPI com wall was now reduced to a single task for that MPI communicator, and MUMPS was actually very happy to solve the problem doing this. Now with a pure MUMPS implementation, what we have is that each task runs a single individual MUMPS solver, and what we could do eventually is to use an arbitrary number of tasks to solve every load, now that we have parallel MUMPS working on this. Essentially what we would do is each of these individual MPI groups that we've created, instead of assigning them a single task, we can assign them several tasks, and that would speed up the code. This is a very simple way to scale up the code. The only problem is it performs pretty bad in terms of throughput, because it never reuses the factors for K. So when we did a typical load test with 320 tasks, this was actually 11% slower than the original, which you might think is not too bad, given that we're not reusing any of the K factors, And if we added now, say, 640 tasks, and we use 2 tasks to solve each load with mumps, we probably speed up the code by about 80%. The problem is that the speed up is not the only thing that the user wanted. The speed up is, in this case, would be at the cost of more resources, and what we wanted to do is make this code more efficient, not just faster. So leaving the project at this point would not be aligned with the objectives of the PI. They would have a simple, scalable code, but they wouldn't have a code that was more efficient than the original.
So, Carlos, just to be clear, so if it ran faster, it would run on more processors and eat up the P's allocation more quickly?
That is correct. So at
Yeah,
this point, you could make the code run faster, but it would have to use more resources. So the code is now scalable, and it wasn't before, because you could only ever use 1 task per load solution, and now you can use as many as you want. But the problem is that we would be using more SUs. That's correct.
Yeah, maybe it positions her to ask for more in the future so she can do more. But yeah, I'll let you keep going.
Yep. So what we ended up with was designing an alternative algorithm to do this solution that consists on factorizing K, which is the static part of the full matrix, solving an intermediate system, ky equals minus b, which b we have to assemble for every load, but now because we have the factors and we're just calling mumps for the solve, we are reusing those factors every time we do this for every load, so we got rid of this problem of never using the factors for the largest submatrix in the system. After that, we just do a couple of a multiplication, a matrix-matrix multiplication, a DGESV solve to get the the F values, and then we can find U with just a matrix vector multiply. So essentially, we end up using mumps to do the largest factor and solves in the system, and then a matrix-matrix multiply and a matrix vector multiply from BLAS, and a DGESV call to LAPACK. And you repeat these as needed for every load, except for the factorization. What these ended up giving us was about a 1.3 speed up for the typical load test that we were working with for development, which was 320 tasks, and 1.2 to 1.6 for typical workloads. So the larger the workload, actually, the better the speed up that we were getting. When she was using smaller loads, she would get a 1.2x, but for larger core counts, she would get better speed ups. What I like about this is that not only she's getting about 60% better performance for her current loads, but she can speed up things as much as she wants now. If she needs to speed up these by a factor of 400%, she can use 4 or 5 MPI tasks for every load with mumps, and she will be able to do that as well. So, in conclusion, in terms of future work, there's a couple of things that can be done. Right now, we do an intermediate step, which changes the shape of the matrix to put it in mumps format, and that's actually costing us a significant fraction of the solving time. So Lorraine agreed that she would probably do this in the future in the code, because assembling the matrix directly in the mumps format would probably save her a good chunk of time, probably in the 10-20% of runtime, depending on how she implements that. There are other things that could be done. If you notice, I've been talking about solving K from every task, but there is actually K is a static quantity throughout the code, not for every task. The only thing that is different for every task is the loads. So we could factor and solve K using multiple processors instead of a single process. Now, the framework is already in place because she has all the framework to work with mumps. So this is a step that she can now take on her own and make the code significantly better. While then we would use those factors in every task to do individual solves for every load. We could also use an iterative solver, taking as the initial solution the solution of the static part of the full matrix, but we haven't actually had time to look into that and profile. So that's something I suggested to her to try in the future after she did the direct assembly of the matrix in MEMS format. There were a couple of lessons that I learned from this project. The first one is that no matter how confident you are that you got your work plan right, after the first quarter you probably know the code much better, and it might be a good idea to spend a couple of days just thinking about, okay, what did I actually promise in the work plan, and what can I actually do with the time that I have? Is it still a reasonable objective? If it's not, then, I think it's a good idea. Talk to the PI, explain, hey, the original work plan that we put up might work, might not. In some cases, you might think that you can do more than you promised, which would be great. In some cases, you might have to redefine your goals and shorten them a little bit. But I think this would be a good thing for everybody that works in ECSS, just to reconsider after the first quarter whether the work plan was adequate. That way you can just change the work plan, resubmit it, and be confident that everybody is on the same page, which is something I didn't do with this project at the beginning. I think I should have. Other than that, probably put more emphasis, and this is for me personally, I assume everybody in ECSS works in a different way, but I think I should put more emphasis on providing the user with examples and spend less time working with their own code. I think it's more instructive, and this is something I've switched to doing, it's more instructive for the user to get an example that says, okay, this is what you want to do, this is how you do it with a trivial example. Try, put it in your code. If you can't, I will help you. And in most cases, they will actually pick it up and do a pretty good job, and also have a reference for things that they do in the future. And that was pretty much all I had today, because I thought I was going to run out of voice while I was giving this talk. So if you have any questions, I'll be happy to take them.
Carlos, thank you very much. Let me unmute the phone line.
Presentation mode is now disabled.
Okay, folks on the call, questions for Carlos, comments on his approaches to the work plan and examples. I think he made some really good suggestions. Anyone care to contrast that with how you've approached some of your ECSS projects? Yeah, I thought...
Hi,
go ahead.
Dmitry Pekhorovsky. I agree with this point, and I had similar experience in my projects. I think it's a good approach to reevaluate work plan and provide users with example. It's just right on.
Thanks.
Yeah, thank you very much. I mean, these could go into just instructions that we provide for our ECSSers also, because with 80 folks, some people are going to come up with really great approaches that don't work their way out into the wild except through talks like that, like this. But that seemed awfully relevant, Carlos. I mean, it really is. We ask for the work plans up front, but you're exactly right. It's impossible to do that without looking at the code. I mean, you might, describe something, but then reevaluating after a quarter sounds totally appropriate.
Yeah, and I get the feeling that even though internally we know it's perfectly fine to change the work plan and redefine it, some people, might have doubts, would it look bad if I do this? But I think it doesn't matter how it looks. It's just a matter of being more efficient and keeping everybody on the same page.
Right. I mean, I can say from the management perspective, we absolutely don't care if you change the work plans. I think it's taking the time to go do it. But you're right. If you take only a day or two and say, this is how things ought to change, and it's really keeping the PI on the same page too, and letting them know what's reasonable over the course of a year. So, yeah, awfully good points there. Anybody else on the line want to jump in?
This is Kwai.
Hi, Kwai. Go ahead.
So I just have a cool question. So you are solving each process is solving a serial problem. So the serial problem. So you sort of had an SPD matrix. You said symmetric. It's definitely symmetric. Is it symmetric?
Yes, positive, definitely symmetric. Yeah.
So it's an SPD matrix. Mm-hmm. So the comment is iterative method should work well, and
yep.
So in the sense that I guess so I'm not very familiar with the problem, but somehow your problem size you use multiple MPI tasks, but is it each task is doing a different parameter study? Is that so, or?
That's so. So if you remember, I mentioned two block matrices, K that was static and B that was changing with every load parameter. So what they have is they're trying to solve an inverse problem. What they do is they have a whole bunch of differently generated loads, and each of those loads is essentially a full finite element problem that they need to solve. So if you used a iterative method, yes, you would be able to use it for every load, but I don't know how you can. I mean, the way that I would think you could speed up the iterative method, because the iterative method would have to solve the full system, right?
Exactly.
So what you could do is, and that was my suggestion to the PI, is use the static factors to get a good initial guess for the iterative method. But we just never got down to implement.
So it's you basically you do a Schur complement and then leave the K matrix by itself, and then do some of the Schur complement recovery. So in the sense that why didn't you use LAPACK in the beginning, so you can store the LU of the or L transpose half of the matrix?
Well, actually, if you use LAPACK for each task, what you get is a significant slowdown with respect to the PI code.
No, I mean just for the K part.
Oh, for the K part, no, we tried too.
Okay.
We tried too, but it ended up being slower overall than using mumps and then.
Okay, I certainly understand that.
Yeah, sorry. Yeah, no, I didn't actually present that part, but we, after doing the single solve with mumps, we tried using exactly the method that you're talking about right now, and that ended up being slower than the original by about 20-30%, and that could be maybe because the way we implemented. I'm not sure. But
so you certainly use no memory. I mean, depends on the format of your matrix that you store.
Yeah.
Mhm. Okay, but certainly you can do the factor, and then the factor will be saved, and then it can be reused for every step, and it should be very simple. I guess it's
So the problem that we had was that if you do this with LAPACK, that's fine. You can recover the factors. Most of the solvers, the factors are not transparent to the programmer, so the factors are calculated, kept in some compressed storage format in memory, but they're never given to you. So as the developer, you cannot just grab the factors to use them later on with a different solver. With LAPACK you can, but with other solvers you can't, or it's complicated enough that it's at the end of the day not worth it because of all the bookkeeping you have to do.
Exactly. So because the months, what kind of format you using? The Skyline format?
Yeah, she's using the Skyline format.
I see.
Which is pretty common.
Okay. Thank you.
No, thank you.
Thank you. Very, very interesting discussion. I think it also struck me, we're just about out of time here, but it struck me, and I think this is probably true of more PIs than we realize, that solving a problem more slowly and conserving an allocation is important to the PIs. Typically, we think of supercomputing, hey, you can solve this really quick. That means you can do much more investigation, but it is true that often requires a much larger allocation. And I hope, I hope there aren't too many PIs that are being conservative in this way. I think it could maybe limit the spaces that they could explore. But maybe you've set her on the right path, Carlos, for some larger requests, since she can now demonstrate
one more
scaling.
comment is if it is solved just serially in certain sense, I guess with GPUs coming, you can use Magma to do some of these calculations, so you can.
Well, yeah, but the problem is you also have to be careful because you want to give her something that is scalable. So you don't want to do the solve in a sequential manner. I mean, right now the results I presented to you were in a sequential manner because she didn't want to use more resources. But at least now she has the possibility of doing so.
Mm.
So, there are many, many options, but you have to be careful that you set her up to be able to do better things in the future as well.
Sure.
And she has a small group of people. I don't think she has enough manpower to get somebody dedicated to learning CUDA and then going on and keeping up with that code on a GPU. I mean, it is a good idea, but I think you have to consider what the PI can do from now on after you leave the ECSS project as well. So if it was a larger group, I would say that's a good idea because they can probably dedicate enough manpower to do that later. But in this case, I felt that it wouldn't be very productive for her later on.
Great.
Very good. Thank you very much. Very good observations, Carlos, as far as the PI's objective and the size of their staff. So I want to thank Kwai and Carlos for taking the time to work up these terrific presentations today. Thanks for all of you who joined us, and we'll have our next call in March, third Tuesday of the month, which I think is also March 19th. So I hope to talk to you all then. Thank you very much.
Thank you, Nancy.
Bye.
Bye. Bye.
Bye all.